In this video, we're going to look at the parallel RLC circuit that is critically damped, or in other words, alpha squared minus omega naught squared equals 0. Recall that alpha for the parallel case is equal to 1 over 2 times R times C, and omega naught is equal to 1 over the square root of L times C. Further recall that S1 and S2 are equal to negative alpha plus or minus the square root of alpha squared minus omega naught squared. So in the underdamped case, alpha squared minus omega naught squared equals 0. The radical is 0, and we get then the values of S1 and S2 are the same value of equaling minus alpha. Mathematicians say that this is a single root with a multiplicity of 2, or it's a double root, or it's a repeated root. However you want to refer to it, we get only one value. Thus, when we let S1 and S2 equal alpha, we have a d1 e to the alpha t, we have an e to the alpha t term here. It only gives us, because they both have this e to the alpha t term, we really only get one term from it. The solution to that you learn in an ordinary differential equations class is that we take one of those terms and multiply it by a polynomial. Any polynomial will do, but the polynomial t to the first power is the simplest polynomial, and that's typically what's chosen. So to get around this problem of having a single root which leads to two identical exponential terms, you multiply one of the exponential terms by a factor of t. Thus, for the critically damped response, v of t is equal to d1 times t times e to the s1t plus d2 e to the s2t, where s1 equals s2 equals minus alpha. So let's rewrite that then. V of t then is equal to d1 t e to the minus alpha t plus d2 e to the minus alpha t. We now have two terms that are different, and we have two constants that we need to evaluate from the initial conditions. We're going to go about it exactly as we have the other times. First of all, evaluating the function itself at t equals 0, we then get then that v of 0 plus is equal to, now when this t term here goes to 0, this entire term goes to 0. E to the minus 0 is 0, and we're left with d2. So our constant d2 is simply equal to the initial voltage on the capacitor. Now let's differentiate the voltage with respect to time. And when we do that, we get d1 times t. Now we have t times e to the minus alpha t. So two different functions of t multiplied together, we need to use the product rule, which is the first one times the derivative of the second. Well, the derivative of the second kicks out a minus alpha term, e to the minus alpha t, plus d1 times the derivative of the first, which is just 1, times e to the minus alpha t. And then we have the derivative of the second one, which gives us simply minus alpha d2 e to the minus alpha t. Now, when we evaluate that at t equals 0, we have dv dt evaluated at t equals 0 is equal to, in this term, we have the t multiplying here. When t equals 0, then this term goes to 0. In each of these two terms, we have the e to the minus alpha t, which when t goes to 0, the exponential goes to 1, and we're left with simply d1 minus alpha d2. And as we did in the past, the derivative of the voltage then can be determined, the derivative of the voltage evaluated at t equals 0 can be determined by taking the value of the capacitor current at t equals 0 and dividing it by the capacitance. So we have two equations. One equation gives us d2 directly, v naught equals d2, or d2 equals v naught, and then the second one comes there.